Now that the motion of our conducting bar is inducing a current in this circuit loop here, we notice that the bar itself could be thought of as a current carrying wire. And we've got a current carrying wire in an external magnetic field. And we know that such an object will feel an electromagnetic force. This is our Philb type force on a current carrying wire. Let's look at that force. So IL cross B, L with a magnitude equal to the length of the bar will point in the S hat direction, the direction of our ds vectors, so L points upwards. In this case, our current points opposite of ds because of Lenz's law. So we see this current would count as a negative current here. So IL cross B, where I is negative. All right, L is upwards, crossed with B, pointing to the right, but I is negative, so that flips it, pointing to the left. We would have this electromagnetic force on our current carrying wire pointing left right there. And a simpler way to think about this, if you're confused about the flipping signs here and the direction of L, is just to note that the combination of the current times that length vector, that combination IL, that always points in the direction of the current. So simply, we could just take the direction of the current crossed with B. So I crossed with B, which is out of the page, points to the left. So there's our force right there. It is opposite the direction of our velocity. So that force is going to be slowing this bar down. It's going to be a drag force. Let's quickly look at the other case. What if we give that bar an initial push to the left? If the bar is being pushed to the left, then we've worked out from Lenz's law that we'll get a counterclockwise current instead. That's because if the bar is moving to the left, we have a diminishing magnetic flux out of the page. So a current will be induced to try and restore outward flux. So this counterclockwise current will be giving outward flux, trying to maintain the flux that was there. Okay, so push the bar to the left and we get a current flowing this way. Now look at that ILB type electromagnetic force on this bar. I times L points in the direction of the current. So I crossed with B out of the page points to the right. This bar is going to feel an electromagnetic force to the right, which is still opposite the direction of the velocity of the bar. So in either case, we get a force that's going to be slowing the bar down. We're getting this electromagnetic drag force. And it also characterizes Lenz's law. This force serves the purpose of trying to maintain the magnetic flux that was already present in this loop. In this case, as the bar moves right, the flux through the loop is increasing. So a force appears trying to oppose that, trying to slow that bar down to stop that flux from increasing. Here, this bar is moving to the left, so the flux through the loop is decreasing. So a force appears this way, trying to slow that bar down to stop the flux from decreasing. So we've seen a few cases now where these Philb type forces show up in current carrying wires in such a way that it opposes the changing flux through the current loop. There we go. So our drag force is sort of serving the purposes of Lenz's law and showing us that electromagnetic inertia in the system. Okay, so we figured out the direction of that force. It's now an interesting question to consider the subsequent motion of this conducting bar. If it has mass m and is subject to this drag force here, then we could apply Newton's second law to it. So let's consider now the mechanics question of the motion of this bar over time, subject to this drag force, which is a function of time, due to this velocity, which is a function of time. We also have this current that's a function of time. Okay, let's look. So N2L for our bar, its acceleration in the x direction will be due to this electromagnetic drag force divided by the mass of the bar. Our drag force coming from this expression will be ILB. If L points upwards, then L cross B points in the x direction. So simply ILB. If I is negative, as in this case, then our force will be pointing in the negative x direction, drag force. So here we go. We can sub in this expression from our previous video in for the induced current right here. And there's our negative sign that we worked out earlier that represents the drag force. It shows that whatever sign the velocity is, our acceleration will be the opposite sign. So if velocity is positive, acceleration will be negative. If velocity is negative, then negative times negative makes the acceleration positive. There's our drag force. And noting also that the acceleration can be represented as the time derivative of velocity. So ax is dvx dt. We can sort of we can rewrite n to l to say that dvx dt is equal to the opposite of combining constants here. We've got a BL and a BL, makes it BL squared. And here we've got the resistance of the circuit, and here's the mass of the bar. Kind of a funny combination here, like a resistance times a mass, a mechanics thing and an electricity thing, but there you have it. Here what we've got is what's known as a first order ordinary differential equation for Vx, which is a function of time. That negative indicates that we've got a drag force here. Whatever Vx is, its rate of change will be the opposite of that. So if Vx is positive, it'll be dvx dt will be negative and so forth. We also call this a linear drag force because the derivative of Vx depends on Vx. It doesn't depend on Vx squared or Vx cubed, it depends on Vx, hence a linear drag force. And this is an equation that we can solve. Let's go through the steps. First, we want to split that derivative and get the Vx's on the left-hand side and get the time terms on the right-hand side. So multiply both sides by dt and then divide both sides by that Vx to get to here, dvx over Vx, and here's the time stuff. And we've collected all our constants over here as well. Next step. Note the dimensions on both sides of this equation. Here we've got a velocity over a velocity, that's dimensionless. So if the left-hand side is dimensionless, the right-hand side must be dimensionless as well. So we know this is a time, therefore this combination must have units of 1 over time. The dimensions of this must be 1 over time. Therefore, the reciprocal of this, Rm over Bl squared, that must represent some amount of time. This combination of a resistance, a mass, a magnetic field strength squared, and a length squared apparently is equivalent to some amount of time. Therefore, let's define our time constant tau to be this combination and replace that with tau, and now our differential equation looks much simpler. dv over v equals minus dt over tau. Set now your upper and lower limits. So we'll say that time is going to go from time 0, at which time we'll have this initial velocity. We had to give that bar a push to get this whole thing started. So we do have some initial velocity at time 0, and we're going to go to some future time t to find the future velocity Vx at that time t. So we're trying to solve here for the velocity of the bar as a function of time. Okay, integrate here, and we get a natural log on this side. Apply our upper and lower limits to get this expression, which we can then rearrange into this expression. And we find an exponential decay for our velocity. Vx of t equals Vx times e to the minus t over tau. There's our initial velocity. Graphing that, we would get this exponential decay. So we give that bar a push, and then it's going to gradually slow down. It'll take forever to come to rest, but it will be slowing down. And this kind of exponential decay is characteristic of that linear drag force I pointed out earlier. A linear drag force always gives you an exponential decay, taking forever to fully come to rest. We could interpret our time constant, tau, this as having some significance here. This sort of is a characteristic time scale for the movement of our bar. This sort of characterizes roughly how long it's going to take this bar to slow down. Like, we know it will take forever to fully come to rest, but this amount of time represents about how long it would take for Vx to drop to a third of its initial value. So this is where t equals tau, right about there. Put in tau for t, we get e to the minus 1. E is about 3, so that becomes about a third. So the velocity is about a third of its initial velocity when tau amount of time has passed. So if you want to stop that bar more quickly, we need a shorter time constant. That'll happen. We get a small time constant if the resistance is small and the mass is small, and if the magnetic field is big and it's a long bar, if L is big. That would give a small time constant, which would stop the bar or slow it down more rapidly. Why is that? Let's consider just the resistance there. If the resistance is small, that means the current will be big. And if the current is big, then our Philb-type drag force will be big, slowing the bar down faster. You can think through how the time constant would depend on these other factors, M, B, and L yourself. One more question we could ask here would be, how far will that bar slide? If our rails extend on for as long as we need them to, will the bar slide all the way to infinity, or will it reach only eventually some finite total distance? We can answer that. If we know that Vx is dx dt, then we can turn this around to say that dx equals Vx dt, and we have Vx as a function of time. That's this function right here. So plug this function in there for Vx, and we can integrate. We can say that x will go from some initial position, x naught, to some final position, x at infinity, where the bar is as time approaches infinity. So and time will go from 0 to infinity. Let's see if this blows up or if this is actually just some finite value. Okay, so left-hand side, this just becomes delta x. Right-hand side, take our antiderivative and we get this. Evaluate this at our initial and final limits, and we find that this all here goes to not infinity, but minus 1. Minus 1 times minus 1 just gives us this. Apparently, this bar is going to slide to a stop, taking forever to travel this finite amount of distance. This must be some amount of distance right here. So our initial velocity, Vx, times this combination of things tells us how far the bar will eventually go. It's never going to get that far. It'll take forever to go that distance. If we graphed x versus time, we would see this. Start at some initial x, and then gradually, asymptotically approaching some final position, slowing down but never quite reaching there. But it's not going to go to infinity. It'll only ever travel that distance at most as this electromagnetic drag force brings our bar to rest.